3 distinct segments are chosen at random among the segments whose endpoints are the vertices of a regular 12-gon. What is the probability that the lengths of those 3 segments are the 3 side lengths of a triangle with positive area? The plan of solving this problem is clear. We must count all segments connecting vertices of a regular 12-gon, calculate the number of all triples of those segments, and then figure out the number of those triples that can form triangles with positive areas. Of course, for that we need to know the lengths of the connecting segments as well. Probably the easiest and quickest method of finding the lengths of connecting segments is to draw the minimal necessary fragment of a 12-gon to scale and measure these segments in centimeters using a ruler. Let's draw a circle with any radius, for example 10 centimeters long, using a compass. Then draw a diameter 20 centimeters long and 5 radii inside one semicircle using a protractor, such that there is a 30 degrees angle between each 2 adjacent radii. This drawing has 7 vertices of the 12-gon that should be enough to draw 6 segments that connect them with 6 different lengths. Let's connect one selected vertex at the top with every other vertex on this diagram with straight lines. This gives us 6 segments that we denote by letters A, B, C, D, E, and F, where F is the diameter. It's easy to see that if we continue connecting the same vertex to other vertices inside the left semicircle, we will get the same set of lengths A, B, C, D, and E due to symmetry. And of course, we will get the same set of lengths if we draw similar segments starting from any other vertex. The measurements of these 6 segments should result in 6 approximate numbers shown on the diagram. Note that the length of segment B is 10 centimeters, that is half of the length of the diameter. This is how it should be. If we connect the respective vertex and the end of the diameter with a straight line painted green on the diagram, the resulting triangle is the right triangle in which side B is the opposite side to the 30 degrees angle. Indeed, the central angle of the respective vertex is 60 degrees, so the measurement of the corresponding inscribed circle is 30 degrees. Now we can count the number of segments of each length and calculate the total number of segments. Since 12-gon has 12 vertices, there are exactly 12 segments of length A, 12 segments of length B, 12 segments of length C, D, and E. And there are exactly 6 segments of length F, since after rotating a diameter 6 times, we obtain the entire set of all diameters. So the total number of all segments connecting vertices of a 12-gon is 66. The number of all triples equals 66 choose 3, which equals 66 times 65 times 64 divided by 3 factorial, which equals 11 times 65 times 64. Now we need to count the triples with side lengths that can form a triangle with positive area. Such triples must satisfy the triangle's inequality, which requires that each side of a triangle must be strictly shorter than the sum of lengths of 2 other sides. The triangle's inequality theorem is a very important fact which is widely used in mathematics. Let's find such triples first that do not satisfy the triangle's inequality, since it might be easier to count. Let's do it by inspection in a systematic order. We'll start with isosceles triangles with 2 sides of length A and 3rd side of length B. See the picture at the top of the diagram. Since A plus A is greater than B, this is a valid triangle with a positive area. The next picture below it demonstrates the case with 2A and C. In this case, the sum of A plus A is less than C. so that two sides of length A are too short and cannot form a triangle with third side C. This is the first bad triple. The top row of our matrix of bad triples includes 4 cases with 2 sides A in combination with sides C, D, E, and F. The next row includes another isosceles triangle B, B, and F, and 3 mixed triples starting with AB. These are ABD, ABE, and ABF. And the third row includes 2 mixed triples that start with A and C. These are ACE and ACF. Note that the precision of measuring the length of segment in centimeters using the ruler is enough to make these results definitive, except 2 cases, B, B, and F, and A, C, and E, because in these 2 triples we have equality. But for the triple BBF, we have already proved, beside measuring, that B plus B equals F, so that this triple indeed is bad. This triangle is a degenerated triangle with area equal to 0. And for a triple ACE, we can also prove the equality. Note that during the AMC test, you can skip this proof and trust your intuition that the proximate equality is true and it's not just coincidental. This proof is not too hard. We can see on this diagram that C is the side length of the isosceles right triangle, with hypotenuse being the diameter of the circumcircle of our 12-gon. And A and E are the 2 side lengths of the right triangle, where side A is the opposite side to the 15 degrees angle. Indeed, the second leg of this triangle, painted green, is congruent to segment E by symmetry. It's very easy to see. These 2 triangles are shown on the diagram to the right of the circle. VPQ is the isosceles right triangle, and VQS is the 1575-90 triangle. These 2 triangles share the same hypotenuse. Side VS has length A, side QS has length E, and sides PQ and PV each have length C. If we draw point R on side QS such that QR has length C, then triangle QPR is equilateral, since angle PQR equals 45 degrees plus 15 degrees equals 60 degrees. So angle PRQ equals 60 degrees, and angle VPR equals 90 degrees minus 60 degrees equals 30 degrees. So that angle PRV is 75 degrees angle. It's the result of subtracting 30 degrees from 180 and dividing it by 2. This is since triangle VPR is isosceles. Thus, angle VRS equals 180 degrees minus 60 degrees minus 75 degrees equals 45 degrees, which proves that triangle VRS is isosceles. From that it follows that the length of RS is A, which proves that the sum of lengths A and C equals E. Now we can calculate how many actual triples exist with lengths A, and C. It's the number of pairs of sides with length A, which equals 12 choose 2, times 12 segments of length C. The same is true for triples of lengths AAD and AAE. The total of these type of triples is 12 choose 2 times 12 times 3. Then we need to add the case AAF, which adds the number equals 12 choose 2 times 6. Then the case BBF adds another number 12 choose 2 times 6. The mixed cases ABD and ABE add 12 times 12 times 12 each, And the case ABF adds 12 times 12 times 6. Finally, case ACE adds 12 times 12 times 12, and case ACF adds 12 times 12 times 6. Thus, the total number of bad triples is 10,080. The rest is arithmetics. The formula for the probability of a good triple is 1 minus 10,080 divided by 11 times 65 times 64 equals 1 minus 63 over 286 equals 223 over 286. The answer is E.